this open system, non-equilibrium dynamical system. As for example, the time crystals that we discussed yesterday. And yes? Oh, that's true. The camera is not looking at me. Okay, thank you. As for example, in these time crystals that we discussed yesterday, we are going to focus here not only in the open time crystals, the boundary one, but also in the closed one. And then I'm just going to review a bit that we went very fast about how MBL could stabilize this phase also in the closed setting. But of course, I mean, when I'm talking about metrology, we'll try to review some basic aspects of these theories, what do we mean by metrology, what's the goal, and how do we approach these techniques theoretically. Okay, so yeah, so I'm just going to split this lecture in these two steps. I'm going to first review what's metrology, and then I'm going to the applications in these phases. So there is this very nice review, actually, on quantum sensors. It goes through many different aspects of these technologies. But essentially, when we say that we want to do metrology, it's because we want to estimate some external physical parameter. And how we do this, we have a sensor, or we have a quantum system, or classical system that we call as the sensor, such that we put this thing in contact to the external parameter that we want to measure. Then the sensor is going to change a bit its configuration, its internal degrees of freedom, such that when we look for how is this change, we try to infer what is the property, what's the external parameter that was making this change there. Okay? Is, for example, in the simplest case, when we want to measure some temperature in our bodies or anything, we just use the thermometer, right? And then we put in contact to the body, and the thermometer is going to change the internal structure, is going to expand, or is going to compress. And then from this difference in the internal structure, we try to infer what's the temperature of the body that you have put the thermometer. And the same idea, the same concept works also in the quantum realm. So the basic steps, then we put the sensor interacting with any signal or physical signal and try to read the change in the sensor and estimate this in the best possible form. So there is actually 4 simple steps, in some sense, that we need to follow in order to use metrology. The first one is that we need to prepare our sensors in some good state, in some good configuration. Okay, such that it can feel better the external parameter that we want to infer. The second part is we put the sensor in contact to the external parameter, such that this parameter theta is going to be encoded somehow in the degrees of freedom of my quantum system here. So here I'm just focused, for example, in closed systems, such that the way that the information is encoded inside my density matrix is given by this unitary. That depends on the parameter that I want to do. But we can also extend these ideas for open systems. For example, we have now the Linibladian that encode now the information on my density matrix that can be as general as possible as well. Okay, given then that the information is somehow encoded in my quantum system, I want to extract somehow this information. So how we extract information from quantum system, we make quantum measurements in our system. The most general type of quantum measurement is what we call as positive operator value measurements. That is, you have a set of operators, such as we did in the Krauss operators. They are one class of POVM measurements, such that when we make the trace of my density matrix to this set of operators, it gives me the probability of each one to be measured in the detector, given that theta was the information encoded somehow in my density matrix. Okay? So this is what we can do in the lab or in experimental settings. You can choose some clever detectors, some clever observables of your system, and then you obtain the probabilities of these guys to be clicked or to be detected, And then you try somehow from these probability distributions that you make many, many measurements, many repetitions of your experiment, you try to decode the information that is implicit in there, and you obtain what is the expected or estimated theta with the uncertainty of this parameter as well, okay? So it's going to depend on many things: how you prepare the system, how the information is encoded there, which type of observables you're choosing. You need to choose clever observables, and also how you make this decoding process here. So you need also to think on different strategies to make this guy, okay? But the idea, or the basic idea, is essentially these 4 steps. So let's just do in a simple example to try to understand a bit more what do I mean by this. And then we put the general formulas in some very interesting bounds related to the maximum precision that a sensor can achieve. So consider an example of just a spin-half particle in a magnetic field. So we have a magnetic field along some direction. Let me call the direction here is just the z direction. And I have a particle feeling somehow this magnetic field, okay? So let's say that the particle is pointing along any direction. If we have this magnetic field that's not aligned to the particle, it's going to change the internal motion of the spin, and we know that it's going to precess along the direction of the magnetic field, okay? So the presence of this magnetic field then induces a unitary rotation around the z-axis that is just given by a phase theta times the magnetic field operator along z acting in my spin. And the goal then is, given that I look for this movement of my spin, how can I estimate the amplitude or the rotation of this magnetic field? Okay, and then we go for the 4 steps of metrology. So the first one is that we need to prepare in a good form the initial state. So let's say that if initially I have my spin pointing along the same direction of the magnetic field, is a terrible initial configuration, because then the system is simply static. It has no movement because it does not feel anything about this external parameter. So what we can do is just rotate a bit this initial state. As for example, we could make a pi/2 rotation along x or y direction, such that the spin now is not aligned anymore with my magnetic field of interest, and then he can start to process, and we can try to infer this property. So given this, it's very easy to see that the second step now, that is given just by the evolution within the encoded parameter, is just going to drive our system now with this theta dependence, that is just my unitary applied to the initial configuration. That is just, if the spin is up, we get a phase that is equal theta over 2. And the spin is down, we get a phase, minus here, and plus here, theta over 2 pointing into down direction, okay? So essentially, apart from trivial global phase, the system now has encoded as a local phase the information about the theta that we want to measure, okay? So now how can we make good measurements to obtain the information of this theta here? So essentially the third step that we have here. So we can clearly see, for example, if we choose the magnetization along the same direction as our sigma z field is useless, right? Because it's only processing along the z-axis, but the amplitude along the z-axis has no relevance in the rotation. So if you look for measurement observables or POVM operators that just look for the probability of the spin to be around up or in the down direction, that are just, let me say, the projectors up and down, is not a good choice because it has no properties of theta inside of it, right? If we make the probabilities of having up or down, given that theta is encoded in my state, that is just making the trace of my density matrix with these operators here, it has no dependence on theta. On the other side, if we look for some observables along the x or y directions, then we can see the movement or the processing occurring there. And then these are going to be some good measurement observables. So let me say I can try to see what's the magnetization along the x plus direction or the x minus direction. Okay, that is just then the the projectors plus minus, where these are the eigenstates of the X Pauli operator. Okay, so if we look then for this type of operators, so let me call this is not good. While this one here will give us that the probability of measuring an outcome that could be plus or minus, given that theta is encoded there, is just the expectation value of my psi theta, let me call it this way, ni, that are the eigenstates, over my psi theta squared. And then we just need to open this thing here. It's going to be some minimal calculations. This is equal to half up plus ni down. That multiply my state, which is up, plus the local phase I theta pointing down. Everything here, the modulus square of it. Okay. Yes? Where is what? I'm sorry? In here, you're saying. So here we're saying that we have a rotation around the z direction. Okay. And then, for example, it's just because we have a magnetic field pointing this direction. If your spin is not aligned along the same direction, it's going to process around this direction, okay? And then we can see this processing by just applying the evolution into your initial configuration, okay? So you see that the evolution do not change the probability of finding up or down, but it just add a local phase on it, okay? And this local phase can only be seen if you look at the x and y direction of your spin, because it's processing around x and y, but the z is simply constant around there, okay? Yeah, so essentially, yeah, it's important to know what's the direction of your magnetic field in here. Okay, so then the probability distribution around x, for example, will have the information on the encoded theta. We just need to make this calculation here, but it's not hard to see, or it's not, you can try later. It's just open 2 line more of calculations. That is just equal half 1 plus the outcome cosine of theta. Okay. what we expect, right? If the measurement is equal 1, theta needs to be 0, is the initial state essentially. But if theta is equal pi, it means that the state now is around the minus direction, and you can never have the outcome ni equal 1, for example. Now you have ni equal minus 1 with probability equal 1 in my state, okay? But it's simply opening this condition here. So now, in some sense, we have the information here. We need to find the fourth step in our protocol, that how can I estimate this parameter? And then we remember that this probability distribution that we obtain, they are somehow stochastic, right? Sometimes we measure ni equal +1, sometimes we measure ni equal -1, but we just need to make an infinite amount of calculations, or the measurement, experimental measurement, in order to obtain the full probability distribution. But the goal here is that what happens if we just have m finite measurements? How can we estimate in the best form this information here in this case? Okay? And for this, we need to think about good estimation protocols or good forms to make this reverse procedure. So, in essence, the question is how to estimate theta given that we have only finite information on my measurement outcomes. So essentially, instead of having an infinite number of measurements, we just have a finite one that gives us the probability of measuring the first measurement. You measure ni1, the second one you measure ni2, and then repeat the experiment many times, given that theta is equal to the value that you want, okay? Of course, that if m is equal to infinity, we can recover exactly the parameter there because we know the equation. But if not, there is still some uncertainty on this protocol. Is it clear, guys? Okay. So a simple method that can illustrate very nicely these ideas here is what we call as the method of moments estimator. That is just looking for the average of these guys. So if anybody is also interested in understand a bit more details, I would say to go to Andrei or Matheus Figber. They know a lot of the details of these methods as well. So a simple method is what we call as method of moments as our estimator. Where we base the concept in the fact that we know that the expectation value of my psi onto some specific observables, let me say the magnetization along the x direction, is just a function of theta. And for this specific case, it's nothing more than +1 when ni is equal 1, plus -1 when ni is equal -1. So essentially, we kill this first term, and the second one here is going to miss only the cosine of theta. Okay? So the expectation value of some observable of my spin, in this case here, is just the cosine of the parameter that we want. That is essentially always going to be a function of the parameter that we want. But this guy here, we can only obtain if we make an infinite number of measurements in our system, if we have an infinite data for the probability distribution. So essentially, we have this thing here that the expectation value of x, theta, is a null quantity. And we know that it has more or less this shape here, and then it keeps going and going. And given then that theta is some value around here, let me call now that theta exact that we should obtain, it's here. It just means that the expectation value is this guy here. Oops. The expectation value when theta is equal to the exact one. Okay. So if we know the exact, we just know what's the function and discover the estimated parameter that we want. But if we have just m finite information, we can look, for example, for the average expectation value of my m measurements. So I look for an average outcome that is just the sum over all of my results, ni I. And from this, we try to infer what's the corresponding theta in here, okay? Which is essentially just making the reverse path for our function determines the expectation value in here, okay? So given that we have then, we have an estimation given m parameters in my theta that is just making the reverse of the function that I already know over my average value, that is just making the inverse of the cosine over my guy, that's the average here. So let's say that I have just 10 measurements of my spin. Sometimes it's up, sometimes it's down, but it's a bit crazy what's happening there. What I do, I compute this guy here. So let me say that is going to be very, very far from the exact one. So this is the average given that I have done only 10 measurements. So my estimation is really poor in this case, right? Because in this case, I would assume that the theta that is in there making the dynamics of my spin is in this place here that is very, very far from the corresponding one. So this one here would be the estimated given only 10 measurements. But of course that if we increase the number of measurements, we should get closer and closer to the exact value. So let me say that now I do 1,000 measurements, then I will be somehow in here with the average for 1,000 measurements, and then my estimation is going to lie much closer to the exact value, okay? And we can make a bit more quantitative statements about how close we are, because if we make the probability distribution of how my average approach the exact one, this is just given by the central limit theorem that it should be always converging there with some variance that depends on the number of outcomes that we have, okay? So if we look, for example, for given the central limit on that region, we know that the probability of the average value given m outcomes will be exponentially close to the exact one. Oops, sigma x exact one, according to a Gaussian whose variance depends 1 over square root of the number of measurements that I'm doing, okay? Yes, so you can even obtain the exact form of this guy for m large enough, and this is just going to be proportional to the exponential of a Gaussian, let me say, around the exact value squared, apart from the variance of my expectation value of sigma x for my initial state. Given, I'm sorry, divided by m in here as well, okay? So in some sense, here is the information of more or less what's the shape of this function here. It comes from the variance. Okay, but we are also going to show that the limit of my estimation is going to depend also on the inclination of this function, or the sensibility of this function to small variations in the x label, okay? Because if we have a function that is just like this, just a plateau, it's impossible to understand what's the estimated value, right? Because it could be either here, 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 they all have the same value. So it's going to depend on the sensibility of your average function that you choose here for the estimated parameter that you want to predict. Yeah. Okay, and of course, I mean, since we have that the expectation value of the average should converge to the exact one, then the estimated value should also converge to the exact one according to a Gaussian distribution. We just need to make the inverse procedure over the probability, and then we would have something like this, that the probability of theta estimated given m measurement should also converge to the exact one that we call theta exact according to an exponential distribution where, again, the variance of this exponential distribution, it becomes smaller and smaller when we make more and more measurements, okay? And this somehow gives the idea how we estimate the precision of our sensor. Is essentially the width of this variance here. If the variance is very small, it means that with high probability, we are really guessing the correct value there, okay? And this is essentially then what we call as the variance of theta estimated given m measurements, okay? And for this case here, I'm not going to show analytically, but it's even possible to show that the variance of this estimated parameter given m measurements, and I just pointing squared here, just to make a formal precise, is always going to be larger or equal to 1 square root of number of measurement, and the second term here that depends on what type of observable that I'm choosing to make the estimation protocol. So the second term here is going to depend on the variance of my observable squared divided by what is the sensibility of the expectation value with the parameter theta that is trying to measure, okay? And then it comes again to your question, right? So if the derivative is equal to 0, you never have a good guess. This is just going to be infinite. However, if you have a very high sensibility when you change slightly the theta parameter, so it means that any small modification in your external field is going to abruptly change the internal properties, then I have a big chance to extract with good precision the theta here, okay? And then this guy is going to be very large, and it means that this guy here is going to be very, very small. In other words, that the width here is going to be really, really precise, like a delta Dirac in the point that we want, okay? Square root of, no, it is square root of m indeed here. Okay, okay. No, yeah, I see. Yeah, it's just we take the square here. Yeah. Yeah, this thing of the variance standard deviation, I always get some typos with this thing. That's true. Okay, so this is just a simple example to grasp the main ideas of these things. But now let's formalize in more details the theory or the general bounds behind the best estimators. Yes?
In this particular example, how would you
So if you think,
You're going to measure the projection of the spin along the x direction.
yes, yes,
And then you repeat that.
many, many times.
Okay, but how do you make it? You wait for some time?
Yeah, so you have different strategies, but the important thing in this measurement here is that they are independent from each other. So for example, you could prepare many different spins and run each of them in a different experiment and obtain the outcomes. So the experiment is just, for example, just to see the magnetization along a specific direction. So you just put, for example, in a non-uniform magnetic field such that you see the deviation in the path, and then you see the click here if the spin is up along the direction that you're trying to do, or the click here if the magnetization is down along your direction. So what you could do, you could prepare many copies of your initial spin, and then you run many experiments or many deviations to have many clicks, for example. Okay? Or perhaps you could make an experiment, and then you see what's the spin of the system, and then you manipulate again your spin in such a way that you try to repeat the same thing. So the important thing is that they are independent from each other. Okay. Usually the best way is that you just prepare a bunch of atoms or an ensemble of atoms. They do not interact, for example, between each other. You put the magnetic field along all of them, and you make a big general measurement on the general spin there. Because everything that you need at the end is just the expectation value, in this method here, the expectation value of a good observable at the end, the average of it. Okay? Okay, so for the general formulas, we are going to call M is the number of independent measurements. And then, as I said, it could be, for example, you prepare either a big state that is just many copies of your same spin, and then you make a big measurement, you obtain M outcomes, or you just prepare one sigma here, and you repeat somehow, let me say, the experiment M times. But in a way that you are sure that every time that you make the measurement, the system collapses, or you can prepare again the same initial condition and repeat the same protocol over and over again. Given that, we are going to call that the joint distribution for my M measurement, just in this simpler notation here. I have done this vector of Ni outcomes, given that theta was my encoded parameter. And I'm going to call as the estimator as this guy theta with a hat, because now it's a function on my outcomes, such that it gives me a value such that leads to a theta estimated value, okay? And then without the heat hat, because it's just a number. In other words, I apply my theta function estimator. In that case, there was just the inverse of the cosine function, for example, onto my variables or my outcomes, and what I produce is the scalar estimated value. And then I want just to impose two conditions, general conditions, for the properties of this estimator here, and see what are the consequences on top of these conditions. And the conditions, let me say that they are pretty reasonable. The first one is just called as consistency condition, that just say to me that if I make an infinite number of measurements, my estimators do lead to the correct or the exact result. So it just say that if I go to the limit when M is equal to infinity, and I look for the function estimator applied into all of my outcomes, it leads to the exact value, let me call here in this way. Okay? But I also want a second condition that is what we call as unbiased of my estimator, such that even if I have a finite number of measurements, on average, it still agrees with the exact value. Is what we obtain there, right? Even if we have a M, we have a Gaussian around the exact value. There is no bias, there is no partiality on the estimator function that we want to see. And then we put just in these words here that the average over my estimated parameter in M outcomes, that is equal to the integral over all of the possible outcomes given theta, and the expectation value of this guy over ni. This is equal to the exact value as well. These are reasonable properties that lead to interesting bounds for the precision of the sensor. So for example, let us manipulate a bit these properties. And then first, let us just take this unbiased relation here and rewrite it in a more simpler form, where I put this right part to the left in such a way that now I have the integral over all of the possible outcomes, the probability distributions that multiply this first guy here, theta estimator applied into my outcomes, and then these guys come to the left part of my integral, and then it appears in here, okay? And all of this needs to be equal 0. This is always possible. I mean, you see that I'm putting theta to the left, it appears in here, but you see that it's multiplying these new terms here. But theta is just a constant, right? It can go out of here, and the integral of the probabilities is always equal 1. So there is no problem to do this. And let me say also for simplicity, I'm just going to discard, to remove this ni here, but it's implicit that it's dependent on my function here as well, just because we're going to be making some calculations. So in order to see this, just because the integral of this guy here, given theta, is always equal 1, because this is a probability distribution. And we can take then the derivative of this function. Derivative of this function. So if we take the derivative of this guy with respect to the exact theta that we want, we just need to do here the chain rule, right? We just make the derivative of this guy times the rest, and then this guy keeps constant, and we get a minus sign from this other one in here. So what we have is that it's going to be appearing now two integrals. The first one depends on derivative of p given theta with respect to theta, and all of the rest appearing here. Theta function estimator minus the exact value. And then when I derive this, I just miss with the integral of the probability here. So all of this minus 1 should be equal to 0. Okay? In order to avoid having another step to the equation, so all of this is just equal 1, I remove this guy here. Much simpler. And this, let me point, this is going to be what we call as a star equation, because we're going to use very soon in the next step of the protocol. Because now we have that all of this thing here is always equal to a constant, and one equation that, or one inequality that appears very, very often in metrological procedures is what we call as Cauchy-Schwarz inequality, that drives to to split somehow this function here in order to see what's the bound for each one of their terms. And the idea somehow you see that here is the quantity that we are interested somehow, is how the estimated value is far from the exact one. And this is going to be some function that is a weird function, and we try to interpret later moment. So we use now what we call as a Cauchy-Schwarz inequality that says to us that the integral of, let me call the x could be anything here, of a product of functions. If I take the modulus square of all of these, this is always smaller or equal than the integral of the first function squared times the integral of the second function squared. Okay? And the idea is that we need to identify this f and g with these two terms in a form in here, such that we have now that each one of them separately is going to be bounded by what happened on the left side in here. A good form to do this is just we call that fx is just the left term in here, so it's the derivative of my probability distribution with theta respect to the theta parameter. And then I put here 1 of square root of p, such that when I define the g function, I multiply also by the square root of p, such that they are going to cancel each other when I multiply in my main function, and then this is not going to appear here in the equality that we want. In the second term is how far theta estimated is from the exact value, okay? So put f times x is exactly everything that is written in here. And then we just expand the right part of our inequality. So in this way, what we have is that this guy here, integral of the ni times all of this, 1 over p, ni derivative of my probability given theta, respect of theta, now squared, because the function here appears squared. This thing multiplying the second term, that's the g squared, the probability, ni given theta, and then how far the estimator is from the exact value square. It's always larger or equal to all of this thing here. That is our main equation from the unbiased property. So everything here is always equal to the star equation, which we know that is always equal 1. So which we know that is always larger than 1. So we can then rewrite with the terms that we want, that we are interested in. So in other words, we can leave this part on the left, that is the integral over all of my space of measurements, probabilities given theta, how far we are, is always going to be larger than 1 divided by all of this weird function here, by the integral over my measurement outcomes 1 over p, theta, and the derivative of theta, ni theta over theta squared, okay? Then we can stop and try to interpret what's happening here. So in the left part here, this is just an integral over all of the possibilities of my outcome and how far the estimator is from the exact value. So this gives us exactly that width or the uncertainty of our estimator to predict the exact value, okay? So this is exactly the variance of theta given theta estimated given m measurements. Is that guy on the right there? That we call this square because also appear in the square form. And this weird function here is what we usually call as classical Fisher information. So it gives us how good is the protocol in order to have a good precision or not, or at least uncertainty as possible, okay? So this is a weird function called as classical Fisher information. Fm, because m is the number of measurements that I'm doing in here. And all of this inequality, you might have already seen in some other cases, called as Cramer-Rao inequality. Classical one is going to be clear why we call as classical one Excel. Okay, questions? Smaller, yes. Yeah, because, yeah, everything, yeah, thank you. Because we always can reach this bound, that's true. So, just one last property before, is that since we assume that the measurements there are independent, measurements, it means that the whole probability distribution can be splitted as a product of the probability distributions for all of my guys here. And then we can see that the Fisher information for m outcomes is just m times the Fisher information for a single function, for a single outcome, okay? And then the Cramer-Rao just goes into a simplification that the uncertainty of it, given m outcomes, is always larger, 1 over square root of m times 1 over square root of the classical Fisher information for a single probability distribution that you use in the derivative or in this weird integral here as well. So in essence, it is really saying that apart from the central limit theorem, that if you improve the number of data that you have, there is the second term here that depends on your estimator, that depends on your measurement observable, and this gives you the maximum bound for any estimator in your protocol. Okay, so this is a very important function in here. Essentially, this is this is one subclass of the Fisher information that you obtain for a specific protocol. But in principle, you could be beyond this limit in here. So I think that here is more or less how far I go from really showing the detailed calculations. Now I'm going to be more general statements, not going to details because we don't have time. But again, I really suggest to look for these two guys if you have more questions, or also I'm very interested to discuss. But we see essentially that the maximum precision for any estimator protocol, it's going to depend, one, in what is the estimator that we are looking for, that we are choosing. It could be the mean value, method of moments. And the other one is what is the set of observables that we're looking. What's the set of I-Ni operators? So from one side, we can show that the maximum log likelihood estimator is the one that really always gets the maximum bound here. It leads to the Fisher information, essentially. So here you have the log likelihood estimator, as the one that maximizes. But this one here is not so simple to show what's the best observable, what's the best set of detectors that you should produce in your system. But then there is this very clever guy that is the Fisher information, and he essentially solved this issue here and showed that you can always maximize, find a specific set, and leads now what is called the quantum Fisher information. That's really the ultimate bound for your uncertainty or for your precision in the sensor protocol, okay? So then for the second step here, if you maximize over all of the PUVM operators your classical Fisher information. So for each set of operator, you have a different distribution probability, and you need to play with these things here. It leads to what is called quantum Fisher information that depends now on your density matrix given the encoded parameter. So I'm not going, as I said, I'm not going to give the details here, but it's again using Cauchy-Schwarz inequalities a few times, and also you use a very clever idea that is called the square logarithmic derivative operator, that you show that there's always an operator that satisfies this type of equality here, that when you derive your density matrix with respect to your estimated parameter, there is a Hermitian operator that kind of anti-commutes with your density matrix, and then you can use a lot this property to show this equality at the end. Okay, I'm not going through details. But essentially now we have the quantum Cramer-Round bound that gives us the best precision where theta estimated times m measurement is always larger, equal 1 over square root of m, 1 over square root of the quantum Fisher information for your density matrix, where the quantum Fisher information for a pure state, for example, it's always possible to show for a mixed state, but for pure is a bit simpler. It's just given by this equation here, where you take the derivative of your quantum state and see how big it is, minus how big the derivative is with respect to only the state squared, okay? Where this guy here, I'm just using the notation that derivative of theta of my psi theta is equal really the partial derivative of theta when theta is inside my quantum state. So essentially we see the idea again of sensor capabilities in here, right? Because it's measuring how big this guy is. If it's very, very big, it means that the Fisher is very large, and it means that the uncertainty becomes smaller and smaller. And this is essentially how sensible your quantum state is to infinitesimal variations of this external parameter. Okay? Should be 4, yes. So that's why I said, please go to this guy. 4, thank you. Okay, so I think that we can make a very simple example here in 5 minutes. That is just, let's revisit the initial example of a particle spin half in an external field. And this particle is not pointing along the magnetic field, it's going to process. Then let me put the time dependence explicitly here because it's going to be important. So the Hamiltonian is just a parameter theta that we want to measure. times the magnetic field, and the induced dynamics, where theta is encoded. Now let me put the time explicitly here, it's just exponential of minus I theta t sigma z. So given that I have initial state, the evolved density matrix is just Schrödinger evolution, sigma minus I, theta t, sigma z, into my initial state. That is just, just the unitary operator acting in my initial state. And to compute the Fisher information, or to see the best precision of this protocol, not this protocol, of this sensor for any protocol, is just need to compute the derivative of this psi with respect to variation of my guy. So the derivative is just, this guy here goes down. It's very simple. So then we have a minus I theta, the magnetic field operator, and psi theta of time in here, okay? Or in other words, let's just put minus I theta, magnetic field, unitary theta time applying to my initial state. So it's very simple to compute the Fisher information for that previous case, for the simpler case. So if we open then the calculations, the quantum Fisher information for this psi theta over t is just going to be the bracket of this guy here. So when we make the bracket, it appears psi initial in here, U dagger. I'm not putting theta or t just to simplify. Then this guy dagger here, plus I times t sigma z. And then the same thing on the right side, minus I t sigma z, u, and my initial state. This is the first term of the quantum Fisher information. So just to simplify, let me put that is equal to 4 here. Okay, so this is equal to 4. And the second term is just plus the modulus of psi initial, this guy dagger, u dagger, and then times this other part here, minus I theta sigma z. Oh, I'm sorry, guys. So this is derivative against theta. So this is t that appeared here, right? And t, it was correct here, but not there. Okay, so t here, and then we have u applied to the initial state. So we see a lot of simplifications now. So u commutes with sigma, and then this guy here is going to be the identity. You see that appear also in this case, u commutes with theta, then there is the identity in here as well. You see that t appears both in this case here as well as in the first case, and in both cases they appear with t squared. So we can also remove the t squared from all of these contributions. And the only thing that is left here is the expectation of sigma z squared over my initial configuration minus the expectation of just sigma z, everything here squared, okay? Which is just the variance of my initial spin on top on my magnetic field that I'm applying to it. So the quantum Fisher information gives a very simple quantification that is just given by how time is going on and the variance of my state into my initial configuration. So you see, it depends on how you prepare. You need to have some variance. It cannot just be along the magnetic field. And also, when time goes on, the Fisher information also increases. This is what we also expect, right? Because when time goes on, that information of the field is getting inside or encoded somehow in the degrees of freedom for a longer and longer and longer time. And then it allows us to have more possibility to extract it at some point, okay? So there is these two interesting dependence on the quantum feature in here. Any questions? Yes?
The fact that you're kind of randomly sampling each time, that's more or less why it looks like it's growing. That's kind of like confusion then.
In which part is growing, I'm sorry?
The quantum Fisher information looks like it's growing as t-squared, which is reminiscent of that confusion, right?
Yeah, it could be. Yeah, I never thought in this way. Yeah, but that's, yes. Because also in the classical, you don't have this thing. I mean, yeah. It depends. Yeah, you need to have some coherence at least. This is what I can say. But it could be because of diffusion. Yeah. Two. So the maximum is when you saturate the variance of your system here. Okay. And the variance in this case here is always order 1. I'm going to this point right now, actually. Yeah. Okay. But there is always a maximum limit for the Fisher information, and this maximum limit is what we call as the Heisenberg limit, but it's essentially when you go to the top of some expectation value or some variance of the initial preparation of your system. Yeah, but very interesting to think about diffusion, yeah, because if you look for a classical particle also, if you look just for a short time, you just know a bit of the track that it has done, right? But if you look for a longer time, you have much more information about the whole trajectory. And since it has also some bounds on how fast this trajectory can be because of diffusion, this is maybe some relation indeed. Yeah. So what about if we have not only a single spin, but now we have a set of n not necessarily independent spins. So now the Hamiltonian with the theta phase acts not only in my first spin, but it acts along all of my spins. So we have theta acting on a global sigma z observable. Two very interesting situations appear in this case. The first one is that if we consider that the initial preparation of my system is just a bunch of separable spins, so they are now completely independent, then the variance of my global magnetic field is just n times the variance of the magnetic field for each one of my spins. Okay? So in this case here, the quantum Fisher information is as we expect, is just n times the quantum Fisher information for just a single particle. It's just a repetition of the same procedure, such as André has asked for us. If you think in a more interesting situation, if psi now, it's not necessarily separable. Now you can have some many-body interactions between your constituents. What can happen in this case? So if you now have some type of entanglement among your spins, so consider, for example, the situation of all of your spins, they might be pointing down, up, but then with a global superposition of everybody pointing down, divided by square root of 2, we know that the time evolution of this guy here is going to have that local phase, but now a phase depends on any particles and not just a single particle. So there's going to appear a local phase here of theta times n times t, and applied to my down spins over square root of 2. And then you see this somehow the enhanced local phase appearing, enhanced phase appearing in my many-body system. In this case then, it's not hard to show that the variance for this initial state in here, it's now the expectation value of s squared the expectation value of S squared in the initial state is just n squared. So S squared into this is just n, S dash this key is just n, so this is an eigenstate. So this is just going to be n squared minus the expectation value of just sigma z that is equal to 0, because it has probability half to be up and half to be down. So this is just n squared minus 0. Then you see an interesting situation that now the quantum Fisher information for n correlated particles, it has the t squared dependence with time, but then you have a squared dependence with the number of particles. And this squared dependence is because now you have many body correlations, or you have a better form to imprint or to encode this information into the many degrees of freedom of my Hilbert space. Yes? You still have a theory of multi-parameters for the Fisher information. It becomes a bit more messy, but yeah, you still have a very close relation there. But now the quantum Fisher information, let me say, if you think in the rough form, the equation for the quantum Fisher information here is going to be a matrix, actually, because now you have a θ1 parameter, θ2 parameter, or θk parameter, many different ones, and then you need to see more or less what are the possible mixtures of these parameters and build something like a Jacobian matrix or the Hessian matrix that you now have a big operator instead of just a number. But you can still use the same ideas in here and build the best protocol as well. Okay, it's very interesting indeed. So in summary, what I try to say that is going to be important here is that if I look for the Fisher information of n particles in entangled systems, it's always going to be better than the quantum Fisher information of n particles, but in a non-correlated system, even though they can be quantum, which is going also to be always better than the quantum Fisher information for any particles, and now you don't have any quantumness, it's just a classical particles. So usually this guy here gives us the bound of t squared n squared. This guy will give the bound of t squared just n, and this guy here is just a central limit theorem and just t times n. So if you want to quantify then what's the potential of a sensor for some metrological protocols, it's good to put in comparison to these three limits here. Where you find your sensor. Is it close to good sensors but still not exploiting correlations, or you're trying to exploit correlations and reach the maximum bound of quantum mechanics, okay? And this is what more or less the comparison that we do in the time crystal to see where it fits. Okay? So, okay, so I would go for the slides right now. I don't know how to put it here. Okay. See? Oh, yes. Can you speak a bit louder, sorry? I think that for pure states, yes. No, I'm not sure, but I would expect so that if you look for example, for entanglement entropy, that's very well defined there. Larger entanglement entropy would means larger quantum Fisher information. And in fact, people use the quantum information as entanglement witness as well. So you can probe not only bipartite entanglement using this relation here. So if you have a quantum system and you compute the quantum Fisher information, if you are on this side of the inequality, you are sure that you have entanglement there. I think that if you have more and more, it will have more and more quantum Fisher information as well. But you can also characterize the form of the entanglement between your constituents. So you can, from the number that you obtain here, you can say how many particles at least are correlated in your quantum system. So you have this thing that the quantum Fisher information for n particles, if it is beyond, let's put t square, just to repeat it. If it's beyond t times, I think it's k square here, if I remember, or t times k, but there is some specific bounds in between this huge bound in here, where this k here is saying the least, the minimum number of particles that are really entanglement in your quantum spin. So you can see some microscopic details as well of your entanglement, multipartite entanglement properties. It's very nice. Yes? Yeah, so I mean, phase transition is excellent for a sensor because you see that the sensor, it depends on the susceptibility of your state to external variations of your parameter in the Hamiltonian. So it depends on the derivative of this guy here. In a phase transition, we know that the susceptibility diverges. So your system is going to be very sensitive to small changes in your Hamiltonian close to a phase transition. And people have exploited a lot this idea to improve your sensor properties or to increase the quantum Fisher information value. Actually, you can show that the quantum Fisher information is the second derivative of the susceptibility of your system with respect to the external parameter that you put. Yeah. So here is t square n square. Here is t square n linear. So here is entangled. Here quantum but not entangled. And here just classical. Yeah, if you have a closed system, yes. Yes. So the T comes really from the protocol here. So if you think just about the state itself, it would not make so much sense talking about T. It's more about the initial preparation and how the time evolving has changed your initial prepared state, okay? Yes, this is the classical, yeah. Because, yeah, so this is just the standard quantum, I'm sorry. Yeah, this is just the central limit theorem. So now T is just the number of repetitions that you're doing in your measurement, and it's just M is another way of parameterizing M number of observations of your system. Okay, and that's why I mean there's no coherence on M. It's just a central limit theorem. Okay. Okay, let me just remove this. But I'm not sure if this is exact the bound, but it has some dependence with K, and K characterize your multipartite entanglement. Any more questions, guys? Okay, I don't think this is work anymore. Neither here. Okay. Okay, so let's use these ideas to quantum time crystals then. So as I said, there is both the boundary time crystal in the last lecture, but there is also some closed time crystals that is called Floquet time crystals. And this is using the idea of this Floquet dynamics, such as Victor has explained us, where you have a Hamiltonian that depends on time, but it has some periodicity on time. And then there is this idea of using a many-body localized system to avoid the determinalization of my system, but still employing some driving coherence to my spins in such a way to have non-trivial dynamics of the microscopic motion. Okay, so what are these operators? Or what's the Hamiltonian of my system? This is the MBL part. It's just eyes in chain with disordered interactions and disordered fields, one-dimensional chain. And this X operator here, it acts at every integer multiple of my time. It makes this big X operation that is just flipping all of my spins around the X direction. So it flips with this 5 phase here, all of my spins simultaneously, around the x direction. So your dynamics is just these two parts. So first, you evolve in a many-body or non-ergodic way, and then you apply the x operator. Then you repeat this again and again. Apply with MBL, flips everybody phase phi. MBL, flip, MBL, flip, and so on, and so on. So let's just take the simplest case where the flip is a pi rotation around the x direction. So if you can expand this, this is the product of sigma x. If you have your spins up, down, up, down, your flipper is just going to map everybody's up to down, everybody down to up, okay? And then we see what we call as the period doubling magnetization for my system. If you look for the magnetization along the x and y direction, they thermalize very, very quickly. You see that they go to zero like an infinite temperature state. But the magnetization along the z direction, that is more or less where the L-bit localized states are pointing up in the MBL Hamiltonian, you see that they persist for a long, long time. And more importantly, the magnetization goes back to itself only after 2 times the periodicity of your Hamiltonian. So then you are breaking the time translation symmetry in a discrete form here, okay? If you look for the absolute value of this magnetization, of course that for finite system, you're going to thermalize at some point. So if you look for the absolute value, it has this plateau. It's where the period doubling, it's appearing here. But then at some point, this plateau starts to decay, your spin starts to dephase with each other, and then it goes to zero to an infinite temperature thermal state. But you see that the lifetime of this plateau here increases exponentially with the number of particles that you are in your chain. And then we expect that in the thermodynamic limit, this thing is just stable, it's just going to persist forever. That's why we have then the formation of the time crystal in my system. What's the idea then? The idea is to get these time crystals, or to get them as our physical sensor, and put them in contact to an external magnetic field that is oscillating, just like this guy here. So it's just a sine function with some frequency pointing along some magnetization direction. And as we did here, we try to estimate the amplitude of this external parameter in here, okay? So essentially, we know that the microscopic dynamics has this period doubling. This is the time crystal that we're going to use. And then the full Hamiltonian evolution is going to be given by the previous Hamiltonian. I'm just repeating it here. But the full Hamiltonian now is given by the time crystal one in here, plus the external field in here that we want to probe the amplitude. So what's the physical picture, or how can we get a good response from this estimation? So remember that the time crystal is essentially this thing here, right? If you have some spins pointing along some direction, they are going to be this stable period doubling dynamics. And on top of this, we are trying to measure this alternating field up, down, and up, down. So a very natural form to think is we need to somehow keep the coherence of the internal motion of my spins in the time crystal with the amplitude of this external field as well, okay? So when the magnetic field is up, my spins are pointing along some direction, and then when the magnetic field is down, my spin somehow feel this movement and keeps the same amplitude or the same internal coupling or the internal direction of this movement, okay? And that's the best performance indeed of the sensor in this case. So we can even think in this previous example here. So when we put a theta phase in the Hamiltonian along the z direction, we get a positive phase in here. If at some point the theta phase becomes negative, then we have a negative phase in here. But then you see that half of the path is positive, and then it's added with negative, and then they would cancel each other. They do not cancel each other because I'm also flipping the internal spins in the time crystal internal dynamics. Okay, so this is really important for the performance of these guys here. So how we quantify or we compare the precision of the sensors, then we compute the Fisher information for the time crystal. And then I'm out setting here in what we call as this period doubling resonance, is when the frequency of the external field is equal half the frequency of my time crystal, and then they have these coherent dynamics, microscopic dynamics between each other. Here's the Fisher information, different number of particles in time. And then I'm already dividing here by t squared times n. That is the non-correlated quantum limit, just to see how much we can go beyond this, or how much the correlations in time crystal can be beneficial for the performance of my sensor. And we see this very interesting behavior in here, right? So if we have more and more spins, the peak here of the Fisher information, or the precision, keeps increasing superlinear with the number of particles. So we are really using somehow the many-body interactions of the constituents to improve the performance. But more interesting here is that you see that the time of operation of our sensor is as we expect from the MBL stability of my system, right? Is exponentially long with the number of spins that I have. So it means that I have these spins there keeping this coherence in a good form to extract the information for an exponential long time. I don't need to every time prepare a new state and run again my experiment. I just need a single shot run experiment, which is going to survive for a long time and encode a lot of information about the field that I want to measure. Okay? So we have this very interesting property. So it saturates the standard quantum limit. It's beyond the standard quantum limit, that is the quantum non-correlated, and survives for a very long time. And this is essentially related to the internal dynamics of my time crystal. Here is the period doubling magnetization. When it is stable, we have somehow a rough plateau in the increasing of the Fisher information. When the phasing starts to be more dominant in the time crystal, but it still is exponentially slow with time, we start to improve even more the Fisher information precision. And then at some point when this thing here reaches roughly 0, it means that the information was completely dephased or scrambled in the microscopic degrees of freedom. And then the Fisher information starts actually to decay. It becomes harder to extract the information now from the evolved state. Yes? Yes, yes. So the entropy is going to be very similar to this guy here. So here's the variance. That is the way to measure correlations as well. But the entropy is going to behave very, very similar to this guy here, that while you are in the period doubling plateau here, you have some correlations that grow, but then they are somehow in a stable plateau. They grow very slowly. It's just the dephasing between the L-beta localized that are playing now. So it's a logarithm increasing with time, the entanglement. But then, as the dephasing starts to be more dominant, the entanglement starts to grow faster and faster. But the interesting thing is that not all entanglement is good for quantum Fisher information. So some entanglement, all of the thermal states, for example, they have a large entanglement. But it can be that in this case, the information is just spread there and you cannot recover this anymore. But in this part here, the entanglement is growing, but also the Fisher information is growing. So it's growing somehow in a controlled form that you can still exploit for the sensor capabilities. This is very nice, yeah. In this case, I'm not sure how to define a quantum thermal machine. But here's a closed system. You would have to think about entropy. Yeah, I don't know. The boundary time crystal, there are some proposals to use as a quantum thermal machine. Very nice. Because it's intrinsically also an open system. Here, yeah, perhaps you could think, but I'm not sure. Yeah. Yeah, but then it's a bit more subtle how to define entropy in this case, yeah. Yeah, and work too, exactly. Yeah. Yes? Yeah, exactly. Yeah, yeah. Perhaps along this direction could be thought, but yeah, I don't know exactly, but yeah, it could be. Yeah. Yes. So this phi here, you say? No, but here can be pretty general, actually, in this case in here. So here is, I know here, I know, it's just because I think that it's just to set, because, okay, this, you have sign here and some phase, okay? But then you need to adjust somehow the phase in here, such that, oops, I'm going to the wrong direction, such that you find more or less the situation here. Okay, so when the amplitude is roughly up, it's when your system is roughly around the fixed direction, and you try somehow to match the up and down in this guy here. The phi is going just to have some dephasing of this block here a bit to the right, and also this block to the right. It's going to decrease a bit the amplitude of the fissure. Exactly, but if you are in the pi, it is the worst case. You are completely dephased and then nothing happens there. But as long as you are a bit dephased from pi, you ought to have some positive accumulated phase occurring in your system. Okay. Yeah, but this is something that I struggled actually a lot with the numericals when I was first doing this numerical calculation. Okay, so, okay, I'm just going to, in 5 more minutes, I think. So if we then do what's the behavior of the fissure formation or the time crystal sensor if we change the frequency of my external field, we see that when they are in period doubling resonance, this is equal 1 in this notation here, it's indeed the peak of the fissure formation. And then it is just the scanning frequency for different times, and this peak keeps growing in double resonance here up to value that increase superlinearly and so on. But what I want perhaps to point out in here is that this is perhaps a second role of the sensor, or a dual role, that it can also work to probe what's the phase of matter that you have there. Imagine that you don't know what's the internal microscopic dynamics of your sensor, but you do this scanning frequency analysis. And you see that in a time crystal, it has this very structured form. So you can try to map this information in order to characterize different non-equilibrium phases of matter as well. So just to be clear, what I'm saying here is that imagine that I'm out of the time crystal. So I changed the period, the phase of the Floquet dynamics so far from pi that now I am in a usual ergodic phase or a thermal phase. We don't see the period doubling here anymore. It just goes to 0 very, very fast. Does not really depend on the number of spins. And here is the frequency scanning again. I change the difference between these two frequencies. And you see the rough, completely disordered behavior, particular of a non-ordered phase as a thermal phase. Okay? So then we can use this dual idea. So in essence, let me just say that for the closed system, we have these different qualitative behaviors. Here is the uncertainty to predict the amplitude of the external field and how it depends on time. Okay? So if we have an ergodic system, the uncertainty decays very, very slowly, much slower than the standard quantum limit or the limit of quantum and non-correlated system. In the red here is the best that you can do in principle according to the fissure formation with non-correlated quantum system. And in blue here is the Floquet time crystal sensor that can go better precision or decrease the uncertainty much faster for a very long time. So in some sense, it gives that there is some potential for this phase to be applied indeed as a quantum sensor. In fact, I think that 2 or 3 weeks ago, there was this first experiments on this idea here that showed that this lifetime can really lead to some good estimation of AC fields. So 2 more minutes, I think, I'm sorry, but I'm going to be fast. Just to show that you can also play with these ideas in the boundary time crystal. Not only the closed one can be exploited as a sensor, but also the open, such as the one that we discussed yesterday, that is the boundary one. We don't care for the bulk degrees of freedom, we just care for the boundary ones. And we have the periodicity of my sensor in there. Then the interesting thing is that here I don't need to set any Floquet dynamics for my internal degrees of freedom. They automatically have this collective behavior between them, and they generate the microscopic periodicity in the internal boundary time crystal, right? And then, again, if we put in resonance this internal motion of the boundary time crystal to the external AC probing field, we see this behavior for the Fisher information here again. So we see that it has this unset description for the Fisher information, which has this growth that depends on alpha, an exponential decay with time. This is the lifetime of my boundary time crystal, and a constant here that also depends on n. But then we see that as we increase n here from 8 to more than 200, we see that the Fisher formation grows for a long, long time, has this superlinear scaling with the number of particles, saying that we are exploiting the many-body correlations, going beyond the non-correlated system. And this you can also check by just looking for how the correlations grow in my boundary time crystal. You see that as you increase the number of particles, more and more correlations are growing among the constituents. One drawback, perhaps, of using boundary time crystals for sensors is because now I have an open system. And usually open system also tend to grow the entropy. We kind of lose a bit of the information faster than in closed systems. And this is indeed happens in the boundary time crystal. So if you look the time dependence here, that in the best case should be t squared, you see that usually for more and more particles, it goes actually lower than t squared. So the entropic constraints are somehow making harder to decode the information from my boundary time crystal. And here is just how the entropy grows with time. So as correlations grow, as the coherence time also survives for a longer time, also some type of uncertainty on the ansatz distribution of my system tends also to increase, and this becomes harder. So we're perhaps thinking, not perhaps, we are thinking how to improve these entropic constraints. Perhaps looking at different type of open time crystals could be better than this specific one here as well. Okay, so given that, go to my conclusions, that I just tried to talk about this metrology, how we use Fisher information, how are the different bounds to classify or characterize the precision of sensors, how we can use these ideas in time crystals in order to improve the performance of sensors, and then we can exploit both the correlations, the collective behavior of my spins, but also that they are both robust. You can have some external perturbations that the time crystal do not care. He stabilizes it again. It's a many-body phase of matter. But also it can survive for a long, long time. So you don't need to prepare the system many times, just a single shot and make the decoding process, okay? Some perspective is looking for different forms of time crystals, how to implement this in the lab. Of course, the lab also has some experimental limitations. We need to take this in account. Here, I'm just talking about the quantum Fisher information. It's just the maximum potential of your sensor. But then we need to say what can be really measured in the lab. Finally, I mean, we have also this different idea of applications as the clocks that I already mentioned, that using this many-body phase to probe, not only to measure time itself, but also to see how these entropic constraints or the quantum thermodynamics would affect also the limitations of this procedure here. Okay, because then we have this constraint from the entropy is growing, we also need to take into account quantum thermodynamic laws. Okay, given that, thank you for your attention. Sorry for passing a bit the time. And questions? Yes?
How did you create this kind of located time?
Create what?
Create these kind of located time crystals in the lab?
Okay, in the lab, you can create, I don't know if I put it here, perhaps in the slides of some other day. No, yeah, I don't have them here. But in the lab, you can, for example, create an effective spin chain using, for example, ion traps. So you have some ions and you use some electric fields that counterpropagating, you just essentially trap one of them, and you can trap in a one-dimensional chain or in different geometries as well, okay? And these atoms, they have some short-range interactions between each other. So you can somehow probe or simulate these effective easing interactions between each other. Not the disordered one in the ion traps, they are actually roughly constant in here between. But then you can apply some external fields to each one of your atoms in such a way that you create disordered potential in here, okay? And then you both create this term here, that is the disordered magnetic field on each one of them, but also you can make some very fast spin echo probes that make a rotation of all of them around some phase, okay? And then you just apply these two steps consecutively, and you create this type of Floquet dynamics in your system. This is one platform. There are many others that have done also the Floquet. There is nitrogen vacancy centers in diamonds. There is superconducting qubits in Google processors or quantum computers. There are many different ones that are very nice. Okay. Okay. Okay, so I think so. Thank you, guys.